This is part one of the lectures covering the seasons. I introduce the seasons to my students in the following way. Compare the position of the sun in the sky at noon on two different days of the year. Say June 21st, and then secondly, December 21st. Now on June 21st, you're going to notice that the sun is very high in the sky at noon on June 21st, as seen, for example, from here in Los Angeles. The sun is very far to the north. Compare that then to the position of the sun in the sky at noon on December 21st. Once again, from here in Los Angeles, you'll see that the sun is much lower in the sky on that day. It's very far to the south. What this then means is that slowly, day after day, the sun from noon to noon moves from the north on June 21st to the south on December 21st, and then back once again to the north, completing an entire year on June 21st. This is referring to the sun's seasonal motion, its north-south seasonal motion. We seek to understand the seasons. Now, at this point in the lecture, I pause and I have my students complete an activity. That activity is called the reason for the seasons. With that activity, the students then simulate what the situation looks like if you could see it from space. In other words, if you can get off the Earth and then just watch what happens as the Earth orbits the sun. If you could, understanding how the seasons work is rather straightforward. Afterwards, however, understanding how the seasons work from the ground, well, that's a little bit more difficult to do. I'll get to that a little bit later on. So as I give this explanation of the seasons here in part one of this lecture, I'm going to be referring to that activity as I go. Okay, now let me go ahead and simulate that activity in the following manner. It's divided up into two parts. I have this light bulb here. I'm obviously using that to represent the sun. I put a piece of paper here in front of the light bulb to cut down on some of the glare, and then I'm going to use this styrofoam ball here to represent the Earth. The students use a tennis ball, and they then stick some pins into the tennis ball to represent different locations on the Earth. Let me go ahead and turn off the lights. Okay, now throughout this activity, let's assume that the disk is the plane of the Earth's orbit around the sun. The plane of the Earth's orbit around the sun is called the ecliptic. And then in part one of the activity, I have the students take the ball and position it such that the equator is parallel to the disk. So the Earth's equatorial plane, then therefore, is parallel to the ecliptic. Okay, now I'm going to use this pencil here, like so, stuck into the ball to represent a specific position on the Earth. And then this right here is called position A in the activity, and I've pointed the pencil such that it's noon at that location. Such that if you were standing here at the base of the pencil, you would notice that the sun is at some angle in the sky. Now watch what happens 6 months later at position C. So I'm going to go ahead and have the Earth orbit the sun. It's rotating like so as it does. And then eventually I get here to position C, and let me rotate the ball such that it's once again noon at the location of the pencil. And then you look at the angle that is made by the sun in the sky, and it's exactly the same as it was 6 months earlier in position A. In fact, it doesn't matter where the Earth is in its orbit around the sun when it's noon at the location of the pencil. Regardless of the time of the year, you're always going to see the sun at the same angle in the sky. Therefore, this Earth has no seasons. So in part one of the activity, I'm simulating a situation where there aren't any seasons, and that's essentially what happens in that portion. Okay, then in part two, we change the situation. In part two, I now take the Earth's equator and I tilt it on an angle, like so, with respect to the ecliptic. And then this right here is once again referred to as position A in the activity. Let me go ahead and stick the pencil in like so to represent a location on the Earth, and it's noon once again. Notice that the sun is very high in the sky at noon at the location of the base of the pencil. This would then correspond to summer. Let's say, for example, it's specifically, however, June 21st. Here's the significance of June 21st. Take the Earth's equator and project it onto the sky, like so, to get the celestial equator. It goes down below the disk in this case. Notice that the light bulb, the sun, is very far north of the celestial equator. The sun reaches its northernmost extent north of the celestial equator on June 21st. That's the summer solstice here in the northern hemisphere. Now I'm going to go ahead and move my Earth here to position C. When I do, I still keep the Earth's equator tilted at the same angle the entire time. like so. And now let me go ahead and rotate the Earth such that the pencil is back at noon. When I do this, however, I keep the Earth's equator tilted the exact same way, like so, the entire time. And now here at the location of the base of the pencil, it's noon once again, but notice how low in the sky the sun is. So then therefore this would correspond to winter in the northern hemisphere. Let's say specifically, however, that it's December 21st. Here's the significance of December 21st. Take the Earth's equator and project it onto the sky, and it's way up here. Notice that the sun, the light bulb, is very far south of the celestial equator. The light bulb reaches its southernmost extent south of the celestial equator, that is, the sun does, on December 21st. That's the winter solstice here in the northern hemisphere. Now, what about the other positions, B and D, on the diagram, which are here and here? Well, let's go to position C once again, like so. It's December 21st, and now let me move to this position here. This is called the vernal equinox. This is March 21st. Because if you now take the Earth's equator and project it onto the sky, notice that it intersects the sun. The sun is crossing the celestial equator on that day, moving from the south to the north as seen from the surface of the Earth. This is the vernal equinox. And then we go once again to here, June 21st, and now to here, about September 23rd. This is the other equinox. This is the autumnal equinox. If you take the Earth's equator and project it onto the sky, once again, it intersects the sun. On the autumnal equinox, as seen from the surface of the Earth, the sun is moving from the north to the south. So the basic cause, or the cause, of the seasons is the fact that the Earth's equatorial plane is tilted on an angle with respect to the ecliptic. The angle that the Earth's equatorial plane is tilted with respect to the ecliptic is about 23.5 degrees. It's somewhat exaggerated, however, here in this simple demonstration. Okay, now also by using this model, that is by watching what happens as the Earth orbits the sun as seen from space, we could see a whole host of other effects associated with the seasons. For example, let's say that it's once again June 21st. And then right here, I'm going to position the pencil at the North Pole. And then watch what happens then over the course of a day. I'm going to rotate the Earth through a full 24 hours. And then we're here at the base of the pencil, that is at the location of the North Pole. Notice that on that day, June 21st, the sun does not rise, nor does it set. You get 24 hours of daylight. In fact, we'll see later on in my explanation from the ground, in a later part of this lecture series on the seasons, we'll see that we actually get 6 months of daylight, 6 months of darkness at the poles, both north and south. Watch what happens now 6 months later when I go here from June 21st to, say, December 21st. Like so. And then we are right here at the location of the base of the pencil. Notice that it is in darkness. And then watch what happens over a 24-hour period. I rotate through a 24-hour period like so, and the sun never rises, nor does it set. It's always below the horizon as seen from the North Pole on December 21st, Therefore, you get 24 hours of darkness. Once again, at the poles, you actually get 6 months of daylight and 6 months of darkness. Notice also, by the way, that the seasons are reversed in the southern hemisphere. I'm still here at this positioning for December 21st. It's winter in the northern hemisphere, but notice, say, down here in the southern hemisphere like so, it's noon at the location of the pencil, and the sun is very high in the sky. So December 21st is the summer solstice, and therefore in the southern hemisphere for this reason. This means that all of the seasons are reversed in the southern hemisphere as opposed to that of the northern hemisphere. Watch what happens, for example, on June 21st. Okay, so June 21st, it's the summer solstice here in the northern hemisphere, but now let's say we're down here in the southern hemisphere and it's noon. Notice how low in the sky the sun is from the location of the base of the pencil, therefore that corresponds to winter. June 21st is the winter solstice then, therefore, in the southern hemisphere. Once again, the seasons are reversed in the southern hemisphere as opposed to the northern hemisphere. Lastly, there are a couple of other lines of latitude that are important when talking about the seasons. I'll describe them in more detail when I then draw out the situations as seen from the ground, but for now, here's a brief explanation of those lines of latitude as seen from space. There is, first of all, what is called the Tropic of Cancer in the northern hemisphere, and then secondly, the Tropic of Capricorn in the southern hemisphere. Here is the significance of the tropics. First of all, the Tropic of Cancer in the northern hemisphere. Let's say it's June 21st. And then let me go ahead and specifically position the pencil here, and now it's noon on June 21st. Notice that the sun is straight up at the zenith. When that occurs, you're standing at the Tropic of Cancer. The reason why it's called Cancer is because the background constellation of stars that the sun is in, the stars are there, you just can't see them because the sun is so bright, but the background constellation of stars that the sun is in is the constellation of Cancer. And now let's go 6 months later, so it's December 21st. Like so. And now let's say we're in the southern hemisphere, but specifically at the Tropic of Capricorn. Like so, here in the southern hemisphere, and it's noon on December 21st. Notice that you look straight up like so, and you see the noonday sun. You're standing on the Tropic of Capricorn. Tropic of Capricorn is at 23.5 degrees south latitude. The Tropic of Cancer is at 23.5 degrees north latitude. The reason why this is called the Tropic of Capricorn is because the background constellation of stars that the sun is in is the constellation of Capricorn. And then lastly is the complement of 23.5. 90 minus 23.5 is 66.5 degrees latitude. That's the Arctic Circle in the north and the Antarctic Circle in the south. Here's the significance of the circles. The circles is a little tricky. Let's say that once again, it's noon here, say at June 21st, and now we're specifically standing at the North Pole. And then, as I indicated earlier, over a 24-hour period like so, the sun doesn't rise or set. Now what I'm going to do is move a little bit to the south of the North Pole, like so, such that my latitude here is 66.5 degrees north. It's once again June 21st. Right here at the location of the pencil, it's noon. Watch, however, what happens at midnight. Like so. Notice that the sun is right on the northern horizon as seen from this location at midnight on June 21st. You're standing at the Arctic Circle. The Arctic Circle is the furthest south of the North Pole that you can be on June 21st and still see the sun for 24 hours. The Antarctic Circle, 66.5 degrees south latitude, is the reverse. And I always kind of have to think about it in order to make sure that I say it correctly. The Antarctic Circle is the furthest point north of the South Pole that you can be on December 21st and still see the sun for 24 hours. That's the significance of the circles. So understanding the seasons as seen from space through this activity and these demonstrations is relatively straightforward. Lastly, however, here for part one of this exercise, how do you then make the leap, if you will, of picturing what happens here from space to ultimately then understanding the situation on the ground? Let me go ahead and turn on the lights to illustrate that. Okay, and I can go ahead and turn my sun off at this point. Okay, so here on the board behind me is the celestial sphere diagram that we have seen previously in previous lectures. Okay, once again with the celestial sphere diagram, you have the Earth here, the north celestial pole, the south celestial pole, and the celestial equator. And then we have, say, June 21st. Like so, which was positioned in this manner in the activity. Where is June 21st on the diagram behind me? And by the way, when I do draw the diagram behind me, let's assume by definition that this line of longitude right here corresponds to noon. So then therefore the sun would be on the meridian as seen from that line of longitude. Okay, now once again, here's June 21st. How do we go from this picture in space to the diagram behind me? Well, merely do this, like so. And now notice that the sun is very far north of the celestial equator. It reaches its northernmost extent on June 21st. So let's say that right here on the diagram behind me, that this position right here is June 21st, and it's noon. And then as the Earth rotates, we would then see the sun trace out its diurnal circle parallel to the celestial equator. Not quite, however, because from June 21st, the sun now begins to move further to the south. So at noon on June 22nd, the sun is not going to be here. It's going to be a little bit further to the south. Noon on June 23rd, it's going to be a little bit further to the south still, and so on and so on and so on. It eventually crosses the celestial equator, however, like so, going from north to south on the autumnal equinox, which is September 23rd about. And then it continues from that point forward. On, say, September 24th at noon, it's a little bit further to the south still. September 25th at noon, a little bit further to the south still, and so on. It eventually reaches its southernmost extent, like so, south of the celestial equator on December 21st, which is the other solstice. Okay, how do we go from our December 21st picture from space from the activity, however, to the diagram behind me? We do so in the following way. Here was December 21st from the explanation from earlier. Once again, here's the celestial equator, and the sun is very far south of the celestial equator. But now take this as seen from space, and just do this. Notice that the sun is very far south of the celestial equator on this day, December 21st. Then on December 22nd, however, now the direction of the sun reverses. So at noon on December 22nd, it's here on the diagram. Noon on December 23rd, it's here on the diagram, and so on and so on. It eventually crosses the celestial equator once again, in this case going from south to north on the other equinox, the vernal equinox, about March 21st. So the equinoxes are here. And then lastly, we continue from March to June 21st like so, arriving at this point here to complete an entire year. I'm going to go ahead and conclude this here as part 1 of this lecture. In part 2 of this lecture, I'll then use this diagram here to go through an explanation of what the seasons look like as seen from anywhere on the surface of the earth.